Hi, thank you for stopping by my poster. My name is Megha Subramanian, and I'm a scientist in the RNAi platform team at Alnylam Pharmaceuticals. I'm delighted to share the work we've been doing to develop a novel RNAi-based rheostat to control AAV-delivered transgenes. Adeno-associated viral vectors are powerful tools for gene delivery in humans. However, managing therapeutic transgene dosage continues to be a challenge. And so having approaches to reduce or fine-tune transgene dosage after the vector has been administered can be a valuable safety feature. In our work, we present a design for an AAV molecular switch that's based on reversible control of RNAi activity. In this system, transgene expression is silenced or dampened using chemically modified siRNAs or vectorized short hairpin RNAs that are expressed in cis from the AAV vector. To induce transgene expression, we use a related technology known as reversir. Reversirs are short single-stranded oligonucleotides that bind with high affinity to complementary guide strands that are loaded into RISC. This blocks activity of the siRNA or the shRNA and restores expression of the targeted transcripts. Importantly, reversirs have a highly generalizable design that can be modified to produce varying durations of responses. In the single agent approach that's described in figures 1 through 5, transgene expression is suppressed by co-expressing an shRNA in an intron within the AAV vector. The viral transcript also contains a complementary target site for the shRNA within the 3' UTR of the transgene cassette. Since expression of both the transgene mRNA and the shRNA are coupled, this sets up a self-regulating system which allows the transgene to be constitutively silenced at baseline. Exogenous dosing of reversir can then be used to block activity of the shRNA and induce expression of the transgene on demand. We demonstrate this using an AAV encoding a secreted luciferase transgene alongside a TTR shRNA that's built into an intron. The self-regulating vector design that harbors both the TTR shRNA as well as its complementary target site shows maintained suppression of secreted luciferase levels in comparison to the non-self-regulating design. Importantly, subcutaneous dosing of a reversir that's targeted against the TTR shRNA leads to rapid recovery of transgene expression that's maintained out for at least 45 days. Since certain applications may necessitate more transient elevations in transgene expression, we also tested a tunable reversir design with lower phosphorothioate content for reduced metabolic stability. In this case, transgene induction is more transient and decays within 2 to 3 weeks, allowing shRNA-mediated silencing to resume. In the dual agent strategy that's described in figure 6, an exogenous GalNAc conjugated siRNA is used to dampen expression of a transgene that contains a complementary target site for the siRNA within the 3' UTR. Subsequent dosing of reversir can then be used to block the activity of the siRNA and control expression in the on state. Here we injected mice with an AAV expressing a secreted luciferase reporter with a target site for a toolkit TTR siRNA within the 3' UTR. Dosing of the TTR siRNA leads to significant reduction in secreted reporter levels that's then recovered in a dose-dependent manner with exogenous dosing of reversir. And so in this way, a dual agent approach has the advantage that it can provide titratable control in both the on state as well as the off state. And finally, for an RNAi-based approach to be feasible, it's important to have highly specific siRNA sequences that can be used to selectively target the virally expressed transgene while minimizing any off-target effects on the endogenous transcriptome. Through a rigorous bioinformatic pipeline, we've identified potential transgene regulator siRNAs that have minimal to no sequence homology to any transcripts in humans or preclinical species. While these siRNAs are intrinsically RNAi active and will potently knock down a target if it's present, they're otherwise highly quiescent and show minimal to no off-target gene dysregulation when assessing their global impact on the transcriptome by RNA-seq. This lack of off-target effects also translates to a more favorable safety profile in vivo, since these siRNAs don't show any significant elevations in liver enzymes at toxicological doses in rats. And so in summary, RNAi represents a unique approach for AAV transgene control, since it has the key advantage of being a clinically validated modality that can provide durable control of transgene expression with relatively infrequent dosing. We believe that this approach could find utility in the clinic as a safety element that can be built into AAV vectors, or as a means to refine transgene expression in case of variabilities in transduction efficiency. Thank you to the team that contributed to this work and to you for listening.